Okay, this video has to do with a titration and then finding some pHs that go along with some things. So anyway, there's a lot of different things in this video. It's a little bit long, but it's very helpful. So anyway, the first thing that you need to do is write the balanced equation for this one. So this is something that you'll have to do. So if you have H3BO3, that's boric acid, plus barium hydroxide, BaOH2. Okay, so the barium will go with the borate. So barium is 2 plus, borate is a polyatomic ion. That's 3 minus, so you'll need 3 bariums for every 2 borates. And then you're going to have the H will go with the H2O over here. So we have H2O. Now you got 3 bariums here, so you're going to need 3 over here. 2 borates here, you'll need 2 over here. Then I always do it that way. Then I do the waters last. So you got 6 hydrogens here and 6 here. That's 6 plus 6 is 12. So you're going to need 12 hydrogens here. Put a 6 there. The oxygens will automatically balance out. Now, we have to write the net ionic equation. So I probably could have written these symbols that these are all aqueous, and barium borate would be aqueous and water will be a liquid. All right, so now to write the net ionic equation, what you need to do is think about, okay, so is boric acid a weak acid or a strong acid? Well, it's a weak acid, so it's not going to dissociate, so you need to keep it together. Keep the 2 in front of it, and so you're going to keep it together. All right, so you're not breaking that apart. Now, this barium hydroxide, what happens is you got this boric acid, so the barium hydroxide, it's going to break down into barium ions, okay, because it's a strong base, and 6 hydroxide ions, and I should write aqueous there. All right, because 3 times 2 is 6 hydroxide ions. Okay, now the salt over here is like an ionic salt. It's going to break apart into ions. They normally do unless they're solids, but if they're aqueous, you can assume that they break apart. Well, we have 3 barium ions, and we have, supposed to be a parenthesis there, plus 2 borate ions, okay, and plus 6 waters, liquid. Now, you can go through and you can cross off any spectators. Well, the barium ion is aqueous, same thing on both sides. But that's all you can cross off. So you just write what's left over is your net ionic equation for this one. All right, so you write what's left over. And 2BO3, 2 minus. Oops, that's supposed to be an arrow there. All right. Plus 6 waters. Now, after you do that, you should see to make sure everything is balanced. So it should be, so we got 6 and 6 is 12 hydrogens. There's 12 there, 2 borates, 2 borates. Okay, so that looks like everything's balanced. But there's one last thing that you can do is 2, 6, 2, 6 can reduce down to, you can get rid of that and put a 1 there, and a 3 here, and a 1 here, and a 3 here. That should, let's see here. Oh, wait a minute here. We got 3, and 3 is 6, and we got 6 over here, so I guess that's right. All right, so that's your net ionic equation. All right, let's move on to the next part of this problem. Okay, so calculate the molarity of the H3BO3. So we have this titration thing here. So we have H3BO3. We're titrating that with barium hydroxide. So the easy way, the fast way to do it when you have an H plus and an OH is you can just use this titration equation, NMAVA equals NMBVB. And so you look at the H, there's 3. We don't know the molarity of that, so that's Ma. Okay, the volume of the acid is 25 milliliters. The OH, there's a 2 there. Remember, it comes from the how many hydroxides, not the number in front when you balance it. Okay, times the molarity of the base, which is 0.080 molar, times the volume that you had to add, that's 29.6 milliliters. So if you do all that work, and you should get that the molarity of your acid is 0.063 molar. I tried to keep 2 significant digits because that's what's given in the problems as the least. Okay, let's go on to the next problem here. Okay, so it says calculate the pH of the original H3BO3. Okay, that's before you titrate anything. So they want to know the original. So what you have to do is you have to write the dissociation equation for boric acid. So it's going to take off 1 hydrogen at a time, and then that's going to give you BO2 minus 1. And I forgot to put the H2 in front. All right. Okay, so that's what you're going to do first there is write that. And you know what? I don't know why I put 3 there, but that should be H2BO3. All right. Okay, then for this one, you're going to need an ice table because it's a weak acid. So we have initial, change, equilibrium. All right, so the boric acid, if you remember from the last part of the problem, originally we figured out that it had a molarity of 0.063 molar. Well, it's going to go down by X when it dissociates. All right, these are going to be 0 initially. They're going to go up by X, okay, plus X. So at equilibrium, we have 0.063 minus X. This would be X, and this would be X. Now, what we can do is we can write the Ka expression. Ka is going to equal H plus times H2BO3 minus 1, okay, all over H3BO3. That's your expression. Now we're just going to plug in the numbers. So Ka, well, here I know what the Ka is. I gave it to you in the problem, so let's just write that. So Ka is 5.8 e to the minus 10. Okay, that's going to equal H plus, which is X, and H2BO3 is X. So instead of writing X times X, I'm just going to put X squared all over 0.063 minus X. Now, since this Ka is a really, really small number, this X is going to be really, really small. So X is much, much less than 0.063. So basically what we can do, because of that, what we can do is we can just kind of drop that X and we can not worry about it. So we drop the X. And so therefore, we can just take 0.063 times 5.8 e to the minus 10, and then take the square root of both sides. And what you would do is you would get that X equals, let's see here, I got 6.0 e to the minus 6. All right, and remember that X is equal to what H plus is equal to. So to get the pH, we can just do this. pH is equal to a negative log of the H plus. And so pH equals a negative log of 6.0 e to the minus 6. So pH will be equal to 5.2. Now, always make sure that your answer, does it sound reasonable? Well, I got a pretty weak acid. It's not very concentrated, so that pH sounds about right. All right, let's go on to the last part. Calculate the pH of the original BaOH2. So barium hydroxide. So barium hydroxide is a very strong base. So what's going to happen is it's going to dissociate completely. But for these bases, I find that it's helpful to have an ice table so you don't forget something. And I'll show you what I mean by that. All right, so the barium hydroxide is initially 0.080. So initial, change, equilibrium. All right, it's going to go down by, see, strong bases dissociate completely, so at equilibrium you have 0 of that left. Okay, you're starting out with 0 and 0 of this, so this is going to go up by 0.080. So at equilibrium we're going to have 0.080. This, however, is going to go up because of the 2 here, 2 times 0.080. And so if you take 2 times 0.080, you're going to get 0.16. Okay, now it's important. We really need our hydroxide concentration. So to get the pH, first we got to do the pOH. So pOH is going to equal a negative log of our hydroxide ion. So we know what that is. So pOH equals a negative log of 0.16. So the pOH is going to equal 0.80. Now, we don't want to stop there because it's asking for the pH. So what we're going to do is use this equation, pH plus pOH equals 14. So we can go pH plus 0.80 is going to equal 14. And so we basically subtract 0.80 from both sides, and we get pH is equal to 13.2. Now, does that sound right? We have a very, very strong base, so it's going to have a pretty high pH. Okay, that's it for this video. You should watch this and then try to do the homework that I assigned to you.